Okay, so we're going to continue our exploration of oscillations by now taking a look at what happens when we introduce forcing, or we can call it a driven oscillator. So again, we go ahead and take a look at the system we've been looking at so far. So I've got a mass that I'm going to, that we'll just say, for sake of arguments, to the right of the equilibrium position. So I'll be feeling a restoring force to the left. Let's also just say for the moment it's moving to the right. So in that case, I'll also be feeling a damping force to the left minus C x dot. But now, in addition to that, we'll have a hand, a motor, whatever. Something is going to take and shake this around as well. This will be some force, arbitrary force, as a function of time. Okay. So we'll again start by coming up with the equation of motion. Mx double dot will equal this force, whatever it is. And then we still have minus Cx dot minus Kx. And we can go ahead and start to work to gain this into standard form. So we'll have Mx double dot plus Cx dot plus Kx equals f of t. Now, just as a fun fact aside, and well, okay, we'll be looking at it as an example later. Remember your LRC circuits? The equation there was given as the inductance times Q double dot plus the resistance times Q dot minus 1 over the capacitance times Q equals the EMF as a function of time. I just thought I'd throw that out there. Okay, so moving along. We need to divide through by m to get into standard form. So let's let lowercase f of t, I guess you could call this a reduced force, although I've never really heard anyone call it that, but that would be what it would be. We'll just let it be that. So when we divide through by m, we're going to have, let's see, x double dot minus c over m x dot, sorry, plus c over m x dot plus k over m x equals f of t over m. And now if we identify the pieces here, that bit right there, remember where we said is 2 gamma. That bit there is omega naught squared. And this whole bit here now is our new lowercase, oops, our new lowercase f of t. All right, so rewriting, we've got the standard form x double dot plus 2 gamma x dot plus k over m x equals f of t. Well, pooh. That is the equation of motion. And in general, this is a bear to solve. Do you remember from differential equations, this is what's called an inhomogeneous equation. In general, they're really nasty to solve. However, the good news is we've already got mostly solved. If you remember, the trick is you solve the homogeneous equation. So the homogeneous part is where we just make that 0 because we feel like it. And we get that solution. And then we have to go back and look at the inhomogeneous equation and by hook or by crook somehow get a solution to that. That particular solution gets cleverly called the particular solution. So you then go ahead and take the homogeneous solution, you add to that kernel the particular solution, and then you've got the complete solution. So we remember, so we've already found, the good news is we've already found in the previous video the solution for the homogeneous equation. So now we just got to go ahead and work on getting the particular solution. All right. Well, we can't really get anywhere without some knowledge of what f of t is. So we're going to make an assumption here, and we're going to assume the driving force is sinusoidal. I promise you that's not as bad as it sounds. I'll touch on that point again near the end of either this or the next video, depending where it gets divided. So anyway, and this isn't so bad, like say if you've attached some sort of motor to a Scotch yoke or something like that to shake it back and forth, this would be exactly your driving force. So we're going to say that our f of t is some f naught times the cosine of omega t. Now there's no subscripts on this omega for once, so this is just the frequency at which we're shaking the mass back and forth. So in that case, our equation of motion will become x double dot plus 2 gamma x dot plus, what the heck was I doing there? That should be reading omega naught squared plus omega naught squared x equals f naught cosine omega t. Now, in general, this looks really bad. You might be thinking, when in danger, when in doubt, run, circle, scream, and shout. But fortunately, somebody very clever came up with a trick we can employ. And that is to just write the equation again a second time. So let's just go ahead and do that. So we'll define a new variable, y double dot, plus 2 gamma y dot plus omega naught squared y equals f naught sine omega t. Now all we've done is shift the origin. So if this has solutions, this first line, this second line in jolly will better have solutions because it only differs by a phase of pi over 2. So this is utterly immaterial to the physical system. This is just a math trick that we're going to employ. Now the next part of the trick here is we're going to take that line and we're going to multiply it by I because I feel like it. And then we're going to add the two of these lines together. So if we let z equal x plus iy, my equation now will become x double dot plus iy double dot, so that would be z double dot, plus, well, we'll have an I here against that y double dot, so it'll be an x dot plus iy double dot. Hey, that's just z dot 2 gamma z dot plus omega naught squared z equals f naught times the cosine of omega t plus I sine omega t. Now that might still not look all that helpful to us, but I promise you it is. Remember the Euler identity here. This is e to the I omega t. So we get z double dot plus 2 gamma z dot plus omega naught squared z equals f naught e to the I omega t. Okay. Well, since there's no crosstalk at all between the real and the imaginary parts, this complex differential equation, if this has a solution here, the black one, the orange one better have a solution, and since there's no crosstalk between the real and the imaginary parts, The blue equation better have a solution somewhere too. All right. So fortunately here now, we can look at this, and what you can do is you can hold your nose and say, well, this looks like an exponential. We know deep in our heart of hearts it's really some sort of oscillatory something or other. But we can look at this and say this looks like an exponential. And so if we guess that our z has some sort of exponential behavior, that probably will work. And so using the time-honored method of solving any differential equation, which is guess and check, we guess a solution of z of t equals some constant, possibly complex, some constant times e to the I omega t. Alrighty ditty, so let's go ahead and stick that in. So z double dot. Alright, so I'll bring down the c 2 powers of I omega squared times e to the I omega t plus 2 gamma. We'll bring down 1 power of I omega, 2 gamma I omega, e to the I omega t. Then we have plus omega naught squared. Oops, I forgot my c here. C e to the I omega t. And that would have to equal my f naught e to the I omega t. Well, that looks promising. At the very least, I can cancel all the e to the I omega t's. So that's a start. So I can factor out a c from the left-hand side. So I'll have a solution if my c times, okay, I squared that, I'm going to get minus omega squared. So I'll have minus omega squared plus 2I gamma omega plus omega naught squared. That's got to equal f naught. Alright, well, that immediately tells us what my c has to equal. My c has to equal f naught over omega naught squared, just rewriting it here to look a little cleaner, minus omega squared plus 2I gamma omega. Alright, and we'll give that, actually we will give that a nice blue star. This will need that in a moment. Alright, well this is some sort of ugly something or other. But it is complex, and anything complex can be written as a e to the minus I phi, where both a and phi are real. So that's good. So this is also part of that same starred thought we'll be revisiting in a moment. Alright, so that gives us some demands. Namely, if I multiply c by its complex conjugate, so c squared, whoops, so c squared, well, e to the minus I phi times its complex conjugate e to the plus I phi is just unity. C squared, which is c star c, that has to equal a squared. Alrighty then, so we know that a squared then is going to be c star c, so that'll be f naught over omega naught squared minus omega squared minus 2I gamma omega, that's the c star. And then the c is the same thing with a plus. Omega naught squared minus omega squared plus 2I gamma omega. All right, so timesing the two together, whoops, forgot my f naughts there. Timesing the two together, I get that a squared equals f naught squared over omega naught squared minus omega squared squared. And then from the cross term, I will end up with, you'd think it'd be a minus 4, but it'll be a minus 4I squared, so it's plus 4 gamma squared omega squared. We're going to identify eventually that A is the amplitude. All right, that's good, but now we got to find phi. Well, if we revisit our friend star, so here what I'm looking at is this and that. This expression and that expression have to be equal, so this is what I'm going to demand right now. So I'm going to demand that A, e to the minus I phi, equal f naught over omega naught squared minus omega squared plus 2I gamma omega. All right, so I can rearrange a little bit, and I can say that my f naught e to the plus I phi, because if I divide by e to the minus I phi, that just becomes e to the plus I phi on top, and just cross multiplying here, will be equal to a times omega naught squared minus omega squared plus 2I gamma omega. Okie dokie. Well, that I can start to pull out. If I look at in the complex plane, that is telling me, so here is the real part, there's the imaginary part, there's my phase angle phi. This piece here is the real part. That will be equal to A omega naught squared minus omega squared. And then here's the imaginary part. So that'll be A times 2 gamma omega. So my phase angle, phi, would have to be the arctangent of that ratio, and of course the a's will cancel. So it'll be the arctangent of 2 gamma omega over omega naught squared minus omega squared. Yay! So, after all of that, we've worked out all the pieces. We have z of t is equal to c e to the I omega t. We worked out that c was e to the minus, was a e to the minus I phi, so I'll just put that in over there. So it'll be a e to the I omega t. Oops. E to the I omega t minus phi. All right. Now, all we ever wanted, if we go way back to where we started, was just the real part of this. The imaginary part went along for the ride just to make the math easier. But now we can go back and say we just want the real part. So that's what we're going to take. So we'll take the real part. And we get x of t equals a, and the real part of this from the Euler identity will be cosine omega t minus phi. Yes, that is our particular solution. So now to get the general solution, we've got to add the complementary or homogeneous solution, whatever you called it, back in. So general solution will be the particular solution, and I'm going to put the particular solution first rather than last because that'll turn out to be physically more important. A cosine omega t minus phi. And then going back a couple videos in our notes, plus some a1 e to the minus gamma minus q t plus some a2 e to the minus, oops, let's try that again, plus some a2 e to the minus gamma plus q times t. And we remember that q was equal to the square root of gamma squared minus omega naught squared, which was the undamped natural frequency of the system. All right. So this part just matches how we're driving it, except that it might be out of phase with how we're driving it. But what do we make of the homogeneous solution? This bit right here in the box. I want you to think about that for a moment, how we interpret that. Go ahead, pause the video, think about it for a bit, and then we'll come back. All right, so if you've thought about it here, what we can do is we can say, well, regardless of whether the Q is real or imaginary here, you're still going to pick, in both of these terms, there's going to be an e to the minus gamma t. So it means that whatever's happening here is going to decay away with time. So we call these oscillations here the transient oscillations, or just the transients. So the moral of the story is, if I start forcing the system, it will first attempt to oscillate in a manner as if it weren't forced, but that unforced part will decay away and will settle into oscillating by following the forcing frequency. So, so the end state is we'll follow the forcing frequency, but at the beginning you can see a little bit of deviation off of that. Okay, let's go ahead and examine. So the transients are interesting, but they're going to fade away. So let's go back to looking at the particular solution here a little more. So we recall that our amplitude is equal to f naught over root omega naught squared minus omega squared squared plus 4 gamma squared omega squared. Take the square root. Okay. So when is the amplitude here going to be a max? Well, the amplitude will be a max when let's try again. The amplitude will be a max when the square root is a min. Well, how can I make that a minimum? Well, I don't know. The one thing I know is that the square root will be a minimum when the argument is a minimum. So I can go ahead and differentiate the argument. So omega naught squared minus omega squared squared plus 4 gamma squared omega squared. I can differentiate that argument and set it equal to 0 and work out when that is. Alright, so let's do that. Differentiating the first term is going to bring down a 2 omega naught squared minus omega squared. Derivative of what's inside is going to bring out a minus sign. Going to give me another 2, so that 2 there now becomes 4. Derivative, then left with an omega there. Then differentiating here, bring down the 2 times the 4 gives me 8 gamma squared omega equals 0. All right. Well, I can factor this. So I can pull out a 4 omega from everything, and actually I'll pull out a minus 4 omega from everything just to make it look a little cleaner. So I will have 4 omega times 2 gamma squared minus omega naught minus omega squared equals 0. All right. And for what it's worth, I can just cancel that 4 away. And so I've got a couple of solutions here. One solution is omega equals 0, which we're going to discard because it's unphysical. The other solution, omega naught squared minus omega squared. The other solution is going to be when this is 0, which will happen at plus or minus, but what the heck does minus mean? And it's irrelevant because cosine of the minus is the same as the plus. So the only physical thing we've got left is square root of omega naught squared minus 2 gamma squared. This is almost the damped oscillation frequency. Recall, the damped oscillation frequency was equal to root omega naught squared minus gamma squared without the 2. So the moral of the story here is, as long as the damping is weak, gamma is much less than 1, the system will resonate very near the natural frequency of the system. Okay, and then if we're off resonance, we can go back to looking here. If we're off resonance, then the denominator will become bigger and the amplitude will fall down. So we can plot that. So let's plot the amplitude as a function of frequency. We'll make that omega naught. We'll assume that gamma is really small. So we'll plot the square because we're probably more interested in the energy anyway. We'll make that 1/2 a squared right there. So if I look at this here, it tends to fall off in sort of a bell-shaped curve around the resonance frequency. And this height right here, we call this width right here the full width at half maximum. So the problem with a bell curve, oh, that looks bad. The problem with a bell curve is that it literally goes on forever. So we have to characterize its width somehow. Actually, let's do that in another color. There we go, much better. And so we just write FWHM, so full width at half maximum. And that gives us some measure of how wide the bell curve is or isn't. Now, what you will show is that these points here correspond to omega naught minus gamma and omega naught plus gamma. But I will be leaving that as an exercise. So now we get a little better sense of the quality factor. If we recall the quality factor, Q was, we found that was equal to omega naught over 2 gamma. We can say that that's the same thing as omega naught over the full width half max. So in a certain sense, it is the inverse of how, or it's a measure of how skinny the resonance curve is. If we only really have oscillation right in the immediate neighborhood of the resonant frequency, the full width half max will be very small, and the resultant quality factor will be high. If it's really spread out, the quality factor will be low. Depending on application, you might want one or the other. For instance, if you're designing a radio receiver, typically you want a pretty high quality factor, so you pick out just one frequency and not, say, an adjacent frequency on the spectrum. On the other hand, if you're designing a bridge, you want the different assemblies of the bridge to have pretty low quality factors so that you're not in danger of any given part of the bridge ripping itself apart. So it just depends on what you want to do. Now if we go back to thinking about the transients for just a moment, we recall that they decay as e to the minus gamma t. So we can say the decay time is 1 over gamma if you quit forcing the system. So going back to that thought for a moment here, we said that the quality factor was omega naught over 2 gamma, right? Let's multiply numerator and denominator by pi because I feel like it. So this will be pi, and then we'll say times 1 over gamma, like so, over 2 pi, and we'll say that that's over omega naught. Okay, so this gives me a pi out front. This 1 over gamma was what we found to be the decay time. And then that's just the period of the oscillation, of the resonant oscillation. So what that means is that if you have a high quality factor, it'll take a comparatively long time for the system to get back to decay back and lose its energy. If you have a low quality factor, it'll lose it pretty quickly. Again, depends on what you're trying to do. Sometimes one's desirable, sometimes the other. Alright, that was a pretty tough slug through there. So let's just go and visit a hopefully familiar example. The RLC circuit. So even though this isn't a mass on a spring, the math is the same, so no reason not to. So we'll imagine an inductor in series with a resistor and a capacitor, and it's all being driven by some sinusoidal EMF source, so LRC. And it's being driven E naught sine omega t. And we want to find, let's go ahead and find the current and the voltage across the inductor. Alright, so we can start with our, by doing Kirchhoff's loop rule on this. So we go around and add up all the voltage drops. Voltage drops are going to be able to have a drop of Li, so LQ double dot, sorry, Li dot, so we'll have LQ double dot there. Have a drop of IR here, so there'll be plus RQ dot there. We'll have a voltage drop of charge over the capacitance there, so there'll be Q over C. So those are all the drops, and then the gain is the EMF source, E naught sine omega t. All right. Well, we can go and put this into standard form. So we'll have a Q double dot. So we find the inductance sort of plays the role of mass here. Plus R over L Q dot plus 1 over R LC times Q. That'll equal the EMF over L times the sine of omega t. So the inductance plays the role of mass, the resistance plays the role of spring constant, it plays the role of damping constant, and 1 over the capacitance plays the role of the spring constant. Alright, so picking out the pieces here, we recognize that this is 2 gamma. That's omega naught squared. And so then this piece here has to be our F naught. And it doesn't matter if we're forcing it sine or cosine, just shift the phase by pi over 2. So we start it up. There's going to be transients, but we're going to let the transients decay. So after the transients decay, our charge on the capacitor as a function of time is going to be A times the cosine of omega t omega t minus phi. And we can work out, we know that the phi, we said that that was the arctangent of 2 gamma omega over omega naught squared minus omega squared. So I'm picking out what those pieces are. They'll be the arctangent of R over L omega over 1 over LC minus omega squared. I can divide top and bottom by omega to make it a little cleaner, and I can multiply top and bottom by L to make it a little cleaner. And we get the arctangent of R over 1 over omega C minus omega L. Okay, and if you remember, 1 over omega C was the capacitive reactance, and omega L was the inductive reactance from before. So, good. That checks with what we knew. How about the amplitude? All right, so the amplitude is going to be, substituting in, we'll get E naught over L, that's our F naught, and then we'll have root omega naught squared, so that'll be 1 over LC minus omega squared, plus our R over L, that's our gamma, so our R over L squared omega squared. Sorry, our 2 gamma squared. All right. So again, I can massage it around a little bit. If I divide top and bottom by omega, and multiply top and bottom by L. I can rework this and get E naught over omega over the square root of r squared plus 1 over omega c minus omega L squared. So that's my amplitude. So then the charge is going to be the amplitude times the cosine of omega t minus phi. All right, but I wanted the current, so let's get the current. The current is q dot, so we'll differentiate that. So differentiating the A with respect to time, this is all a constant here, and we have times cosine, so the derivative of cosine is minus the sine, so it's going to give me minus E naught over, and then I have an over omega, but when I differentiate the cosine, I'm going to bring out an omega, so it's just going to cancel. So minus E naught over root r squared plus 1 over omega c minus 1 over, sorry, minus omega L squared, take the square root, times cosine omega t minus phi. Or sorry, times sine. Omega t minus phi. Okay, so this is r squared. That's xc minus xl. Square it. So we identify the thine in the denominator as the impedance. So, okay, that's working out like we expected. All right, so then to get the voltage across the inductor, that will be equal to L di dt. So we can differentiate all that again. So when I differentiate the sine, I'm going to get cosine, I'm going to bring out an omega. So I'll get minus omega L times the EMF over the impedance, r squared plus 1 over omega c minus omega L squared cosine omega t minus phi. Woohoo! Now, if you want to find where you would have resonance, we could differentiate the inductor voltage with respect to omega and demand. That would be demand we have an extremum, so the derivative would be 0. And I will just assert that you will get that the resonant frequency is 1 over root LC minus r squared c squared over 2, which differs from the L. Remember, for an LC oscillator, it's just 1 over root LC. So this is what you get because of the damping due to the resistor. Okay, in the next video, we're going to go ahead and take a look at a couple of different things. We'll introduce the method of successive approximations, and then we'll also go and take a look at phase space and chaos.